we introduce WANDR, a generative model that generates realistic motions of 3D virtual humans autonomously navigating to and reaching for arbitrary goal locations in space. Human motions are driven by goals. Even simple goals can give rise to complex motions. Reaching for an object requires the coordination of the whole body in order to navigate close to the goal location, orient towards the goal, and finally reach for it. Given an initial 3D human pose, a goal location, as well as the time to reach the goal, we tackle the task of generating a natural motion where the virtual human navigates to and reaches for the goal with its hand, just in time. Current methods approach this problem by either implementing reinforcement learning or training on datasets focused on the problem of reaching goals. Reinforcement learning approaches fall short in terms of motion realism, while being sample inefficient. Existing datasets that focus on the problem of reaching goals, like Circle, are limited in terms of motion variety, and, thus, training on them produces low-quality motions that fail to generalize to novel goals. On the other hand, diverse datasets like a mass have a large variety of motions but lack explicitly annotated goals. To address this lack of data, we need a method that learns from both sources of information while being able to combine them during inference. To tackle this challenge, we propose WANDR. WANDR is a conditional VAE that auto-regressively generates human motion frame by frame. At its core, the VAE learns to auto-encode differences of adjacent poses. In order to guide the virtual human to reach for the goal, each frame of motion is generated conditioned on the current pose, as well as a set of novel features that we call intention features. Intention features comprise of 3 components, each guiding the human character to reach the goal with its hand, orient itself towards it, and navigate in close proximity. During training, the intention of a pose is calculated based on a future pose. It consists of the wrist's average velocity, the change in pelvis translation, delta, and the orientation difference between the future and current pose. In cases where the goal-reaching pose is known, we use that to calculate the features. In cases where the goal label does not exist, we use a random future pose. At test time, where only the goal location is known, the pelvis and orientation intention features are calculated so that they translate and orient the body towards it. The wrist intention tries to guide the hand to touch the goal. During inference, WANDR is able to generalize to novel goals, never seen during training, with generated motions being natural and diverse. Intention features provide active closed-loop feedback that guides the character to orient itself towards the goal, approach it, and reach for it. The virtual human is able to reach near, as well as longer-distance goals, regardless of the orientation of the initial pose. Observe the fluctuation in the magnitude of the wrist intention vector, here visualized as the blue arrow. It dynamically varies based on the relation between the distance to the goal and the remaining time to reach it. For example, given the same amount of time, the virtual human will walk faster in order to reach a goal located further away. And it will walk slower, given a surplus of time for the same distance. Since intention features are computed during the generation of the motion, WANDR can also naturally adapt to cases where the goal changes dynamically. It is capable of reaching different goals sequentially, one after the other, and even go after moving goals. Notice how the orientation intention vector, here visualized as the orange vector, is dynamically orienting the human towards the goal. In addition, the smooth latent space provided by the VAE allows us to perform post hoc optimization and morph a motion to pass through designated waypoints in space. To validate our hypothesis that both a mass and circle are necessary, we also train WANDR using each dataset alone. We observe that WANDR trained on a mass can produce plausible motions, but they lack task-specific skills like slowing down in order to reach for a goal. Training only on Circle, on the other hand, does not result in realistic motions since there is not enough motion variety in the dataset. We validate our model across a wide range of goal locations of various heights, distances, angles, and starting poses. WANDR is able to consistently reach goals located at any angle between 0.5 and 5 meters away. We also observe that it performs better on goals that are closer to the natural position of the wrist. For more details, please see our paper and supplementary material. Our models and code will be available for research purposes. Thank you for watching.